Dear student, today we are discussing about the theorem of moment of inertia. That is, there are basically two theorem of moment of inertia. First is that is perpendicular axis theorem, and second is parallel axis theorem. This theorem is like basically help us to derive the equation or derive the moment of inertia of different shape body, because in our question there is not always like planar body or that equal mass sharing body, just like we are talking about disk, or we are talking about the linear or uniformly massed distribution any body, but we are discussing here the moment of inertia of a body. Okay, so firstly I am discussing about the that is perpendicular axis theorem. So actually moment of inertia having two theorem, that is perpendicular axis theorem, and second is parallel axis theorem. So first of all I am discussing about the perpendicular axis theorem. Okay, so we are discussing with the perpendicular axis theorem part. So what is perpendicular axis theorem? So first part, that is perpendicular axis theorem. So what is perpendicular axis theorem? We are discussing about the, firstly I discuss about the theory part. So it is applicable only for two dimension two-dimensional body or plane luminous. Okay, so we are discussing, suppose I have a different shape of body, any like this type of shapes, y, x and z axis. So among them, we are talking about, suppose the moment of inertia of this will be, suppose iz is equal to ix plus iy. This is the moment of inertia along x-axis, along y-axis, where ix is the moment of inertia of the body about x-axis, where iy is the moment of inertia of body about y-axis, and iz is the moment of inertia of axis about z-axis. Okay, so suppose if I am talking about iz is equal to ix plus iy, then what this mean? That is along xy plane, moment of inertia along xy plane. If I am talking about ix equal to iy plus iz, that means moment of inertia along yz plane. And if I am talking about y is equal to, that is ix plus iz, then along xz plane. This is the point which is very important here. And one more important thing is that note point which have to mention there, that is applicable only for 2D bodies, and cannot be used for 3D, bodies. Okay, but the problem is that in this type of theorem, we must know about the moment of inertia of at least any two body, then only we are getting the moment of inertia of third body. We'll discuss further some numerical part here, so that you understood very easily what is going on in this part. Okay, now next theorem is we are discussing about parallel axis theorem. So how the parallel axis theorem is work, we are discussing about that. Okay, so from this part, next theorem is parallel axis theorem. Parallel axis theorem, and this is valid for all type of bodies. This is valid for all types of body. Okay, so first of all I am discussing about the definition of this parallel axis theorem. Then we are discussing about the no, mechanism of this theorem. Okay, so first of all I am talking about moment of inertia of a body about any axis is equal to the any axis is equal to the moment of inertia about a parallel axis passing through the center of mass center of mass plus product product of mass of the body and the square of perpendicular distance between this two parallel axes. Okay, this is the point. Now, so what are the mechanism, how it works? So suppose I am saying to you, we have this body. Suppose any body we have, like not a circle, like this type of body. So in this body, and I am saying to you the center of mass, the moment of inertia of center of mass, I center of mass is this. So once I know the center of mass, moment of inertia of center of mass, so from this point, this is the center O, into any other point. Suppose from this point to any other point. Suppose at this point, this is the parallel lines at distance d. This is the parallel axis. Okay. Parallel axis. So I center of mass is equal to I of this axis, I center of mass plus that is md square. In many book it is written as I center of mass plus mr square. This is the moment of inertia at axis. That is, suppose this axis is a and b and this axis is y and y dash. So moment of inertia of y dash is this one. Okay, so this is a very basic theorem which we are discussing. But now it's time to, like, use this theorem to both theorem and try to solve some problem on this part. Okay, so first of all I am discussing about the moment of inertia of a rigid body. So moment of inertia of a rigid body. So first of all we are discussing the definition, that is for a continuous mass distribution such as observed in a rigid body, we replace the summation of I, that is summation of mi ri square, I is equal to 1 to n, by an integrals. If the system if the system is divided into initial element of mass dm, and if r is the distance from the mass element to the axis of rotation, the moment of inertia is, that is, suppose there is a mass distribution this, and from here certain point at the distance of r, this is the dm mass. So the moment of inertia is equal to I into dm integrals. This is the formula. By this formula we are able to find the value of, that is, moment of inertia. Okay, where integral carry the overall system, where the integral is carried out over the system. Now, next topic is, on the same basis, we are talking about moment of inertia of uniform rod, uh, about a perpendicular bisector. Moment of inertia of uniform rod about a perpendicular bisectors. Now, so in this part I am talking about, assume the rod of mass m, let uniform rod of mass m and length l as shown. So I am making a rod. Suppose this is a rod and we are talking about the perpendicular bisectors. So from this is the point, okay, from this point to at distance x, I am taken a small element of, that is dm, and the whole length will be divided into two parts. Suppose this is l by 2 plus l by 2, and this is, that is, minus l by 2. This is O point. We are discussing about integrate this moment of inertia of uniform rod about their perpendicular bisectors. So in this part, let the uniform rod of mass m and length is l, where the total mass of rod is m and length is l. We are going from the origin, that is the moment, the perpendicular point. At the distance of x, I am taken dm element. So mass per unit length of the rod, mass per unit length of the rod will be how much? That is lambda is equal to mass by length, that is lambda. And second part is, so that the mass of element, that is dm is equal to, formula is lambda into dx. So we can say that from here, that is dm is equal to mass by length into dx. So according to given formula, which we know about that, moment of inertia I is equal to how much? That is dm into x square under root. So we can say that that is m by l into x square into dx, and the limit is from, that is minus l by 2 to l by 2. So the moment of inertia I is equal to how much? That is m by l is the constant part we are taken outside, minus l by 2 to l by 2. This is x cube by 3, and this is the limit part of this. So when we solve this, m by l is the outside. This is how much? L power 3 by 8 minus of L power 3 by minus minus plus, that is 8 divided by 3. So this will become how much? I is equal to m L power 3, that is into 2 divided upon, that is L into 8 into 3. This cancel out 4, and L is cancel out, that is we can say that m L square by 12. So this is the moment of inertia at centers. So moment of inertia of rod at center of mass equal to ml square by 12. This is the first part, and this is a very important formula, because many times this formula is asked. Okay, now in the second scenario, talking about the second topic, that is moment of inertia of a rectangular plate about a line as shown. So we are talking about rectangular plates. In this rectangular plates, the moment of inertia about this point is now. Here this is the A and B point. Okay, and we can say that the side of this will be how much? The side of will be suppose L, and this side will be the B, that's width, L and width. Okay, so again in this part also I am going from the centers, that is at distance x. I am taken a small element here. This is the small element of dm, and total mass is m. Okay, capital M. So in the same part, in the same case also, what is the moment of inertia? So moment of inertia, that is I along AB is equal to, on the same plate, that is ml square by 12. Okay, and we can say that here, we can say that from here, that will be that at the place of L, we can say that here the L will be replaced by B, so that is ml is mb square by 12. This is the formula here, that is mb square by 12, and B is the width of the this rectangular plates. Okay, now how this formula comes out? If we are talking about the that all part here, so we are discussing in this small part. So we are deriving this equation. So if it's mass per unit length, that is lambda is equal to m by L. So we can say that m by L become how much? That is B into L. That is L into B area, because in this part this is the area. So we derive this equation of this moment of inertia here, that is y mb square by 12 only. So first of all I am talking about is its mass per unit area, that is m by b into L. How it is possible? Because it is the area na. So this sigma is equal to mass by area, and area of rectangle is equal to b into L. B is the width and L is the length of the rectangle. Okay, now second part, we are talking about the area of small strip. So mass of the strip, which strip? That is we are talking about this strip, mass of this strip will be, that is dm. The dm is equal to, the formula is equal to m by b into l. So we b into l into b into dx, b into l into b into dx. So the b and b is cancelled out. The formula become m by l into dx. This is the formula here. So we are putting the same formula in the case of moment of inertia part. So I is equal to how much? That is minus l by 2 to l by 2, and the formula is ml x square by into dx. So when you solve this formula become again same as the rod which we are getting from there. So the moment of inertia of the plate about the line parallel to the other edge and going through the center may be obtained may be obtained from the formula that will be by replacing L by B. So we can say that I is equal to mb square by 12. This is the moment of inertia of the rectangular plate which we are discussing right now. Okay. Now when we're talking about this next part, that moment of inertia of a circular ring. So what is the moment of inertia of circular ring? So the next third point is moment of inertia of circular ring about about its its axis. Okay. So moment of inertia of circular ring about its axis. So we are talking about, suppose we assume that assume radius of ring is r and its mass is m. Okay. So as all the particle of the ring at the same perpendicular distance, so we can say that as all the particle of the ring are at the perpendicular same perpendicular distance are from the axis. The moment of inertia of the ring will be I is equal to how much? That is r square into dm. That is r square into dm, and we can say that this is r square is common and dm will be taken outside. This is mr square. This is 0 to m. So the moment of inertia about center of mass of ring is mr square, and this is very very important formula, many times used in the numerical. Okay. And how was the ring look like and what are the ring? We are discussing about the diagram also. So once so rings is look like this. We are talking about this part. Okay. Now next is, that is a moment of inertia of circular plate. So moment of inertia of a uniform circular plate about its axis. About its axis. So again, the assumption will be same. Let mass of plate be m, and its radius is r. The the center is at O, and the axis OX is perpendicular to the plane of the plate. So we are talking about this part. This is the point, this is the O point. Okay, from here this is the R, capital R, and this is the at distance x, the point is, that is dx. This is the element of dx, and this is the point where x line lies. Okay, so I is equal to, the formula is I is equal to mr square by 2. This is the formula of moment of inertia of a disk, and this formula is also very popular and used here. So firstly I derive this formula. So how to derive this, let's see. Okay, now it's, the derivation will be its is mass per unit area, that is m into pi r square. Okay, so mass of the ring is equal to m by a. Okay, into, that is 2 pi into x into dx. So this will be how much? 2 into mx dx by r square. So once we like derive this formula, so what is dl value here? Dl is equal to 2 into mx into dx divided upon r square into x square. So the moment of inertia I is equal to how much? From 0 to r, that is 2m by r square into x cube into dx. Okay, so this value become how much? mr square by 2 after solving the integral part. So this is the mr square by 2 moment of inertia of the ring. Now next point is the moment of inertia of that is hollow cylinder. Moment of inertia of hollow cylinder. So what is the moment of inertia of hollow cylinder we are talking about here? That is, let r be the radius of cylinder and m is mass. Okay, so as shown in figure, so this is the hollow cylinder. This is the hollow cylinder which we are seeing that. Okay, so about this point, okay, this is the point. So I is equal to how much? Again, r square into dm from 0 to r. So we can say that, so 0 to m, that is I is equal to how much? That is r square into dm from 0 to m. So r square is equal to how much? The value become dm, integral from 0 to m. So I is equal to how much? That is mr square. And this value become how much? R, and the mass will be m. Okay, for solve that hollow cylinder. these are the points. Now okay, so what is the moment of inertia at this point? Means if the particle is rotating at here at this point, then what is the moment of inertia here? So now we are taking the element of x from this part, and we are taking the element dx from here. Okay, so and the length will be, the total length of this rod will be L as the previous we are taken, and the mass will be how much? M, capital M. So we are discussing about the moment of inertia of this whole rod. So I is equal to how much? Again the formula r square into dm, we know this formula. So we are putting this, that is x square from 0 to L into m by L into, that is dx. Okay, so when you solve this formula, so we can say that I is equal to how much? That is m by L. The limit is 0 to L because this is the origin point now, and this is the total length of L. So we are taking the limit of, the lower limit will be 0 and the higher limit will be L, that is maximum, into, that is x square by 3 from 0 to L. So we can say that this is ml square by 3. This is the formula which we are getting from this part. Now this formula we are also deriving by the help of perpendicular axis theorem, and we see in the further how we are deriving this formula. Okay, now one more for the question we have, that is, suppose the question will be moment of inertia, of moment of inertia of rod about an axis inclined at an angle theta with the rod and passing through one end. Okay, so now in this part we are discussing about the that is a different scenario will given in the question, that they are given to you that moment of inertia of a rod, those who are not like, this rod will be a little bit angular. Okay, so what I am saying that this is the plane, and about this plane the rod will be kept in like this. Okay, and these are the angle theta. Length of the whole rod will be how much? That is L. So from here, at the distance x from here, we are taking a small distance of dx. From here, at the distance x, we are taking a small distance dx, and from here to here the distance will be r, smaller. So I think we know about that. This part is the nothing but a right angle triangle like structure. So we are trying to find the, according to given figure, I know about that. This is a right angle triangle. I make here right angle triangle. Okay, this is value is r, this is angle theta, and this value is x. So what is sine theta? Sine theta is equal to r by x. So what is r? R is equal to, that is x sine theta. So for the moment of inertia portion, okay, if you're talking about moment of inertia of this rod, so we know the formula r square is equal to I into dm. So at the place of this, that is x square sine square theta into dm. Okay, so when we put the value from 0 to L, we can say that this is how much, what is the value here. Now what is dm here? Again dm is same as the previous one which we are deriving here. Dm is equal to, what is, that is m by x into m by L into dx. Okay, so we are putting the value here, that is m by L sine square theta into x square into dx. Okay, x square into dx, and integration from 0 to L. So from finally we are getting ml square sine square theta by 3. This is the formula here for the any angle, and about the diameter of a ring. Okay, so in this case we are using the perpendicular axis theorem. By this theorem we are deriving the equation of moment of inertia of ring. Okay, so how we are using the perpendicular axis theorem? See here, suppose first of all I am drawing the ring. A ring is approximately look like this, and this is the another part of the inner core of the ring, that is approximate this one. Okay, so suppose this is the ring, just I am making the ring. Okay, now from here I am saying that this is the inner part, that is y z and Suppose this is z and z dash component, and about the diameter we are finding the value of moment of inertia. Suppose this is id and this is id, okay, and this is suppose y or y component, and this is x and x dash component. So according to figure we know that I z z is equal to I y y dash plus I x x dash component. Okay, so what is the moment of inertia here? So the moment of inertia of this z component is mr square. We know about this formula. This is mr square. Okay, about this part, and this is how much id plus id. We all know about that. This is id plus id. So what is id? Id is equal to I x x dash is equal to I y y dash, that is equal to how much? That is mr square by 2. So the at the diagonal part, the moment of inertia of ring will be how much? That is mr square by 2, and this formula is very very important here. The moment of inertia, now the question will be, next question will be the moment of inertia about an axis tangential and parallel to the diameter of the ring. Parallel to the diameter of the ring. Suppose this is the diameter, one of the diameter, and according to this there is a parallel line. So this is the ring, and I am removing the further part. Okay, this is the ring, and this is the radius of the ring, that is r. R is the ring of this. Okay, now by the help of parallel axis theorem, easily we are getting the value of this. So in the parallel axis theorem, I can say that I, that is tangential, that is we can say that it for tangential. I tangential is equal to how much? That is I diameter plus, that is mr square. Okay, so I diameter is mr square by 2 plus this is mr square. So the formula is 3 by 2 mr square. So through tangent will be, I tangent will be how much? That is 3 by 2 mr square. This is the formula here, and that is very very important. Okay, now next point we are talking about, that is moment of inertia about the parallel to the center of mass. Okay, so next is moment of inertia of ring, moment of inertia of ring about tangent parallel to I center of mass, moment of inertia at center of mass. Okay, so now again